Okay. Hi, everyone. Is there any question from the previous session that you would like to ask or discuss before we continue? Anyone has anything to say? No? By the way, I remind you that asking questions, participation in the class, and also discussions definitely will have bonus points. So I encourage you to please participate in the class and ask your questions, answer, discuss, and anything. Okay, so if you have any question, please let me know before I start the session. Let me share my screen. No, before I share a screen, I should let you know about the assignments and your TA. So your TA is Shafahat Ali, and his email address, I will put his information in the chat. So, someone has asked a question. Let me answer the question, and then I will let you know about the TA. So someone has asked, please explain convex hull once. Sure. So sharing my screen, I can say that convex hull yes. So what convex hull is that assume we have some set which might not be necessarily a convex set, right? So what was the convex set? We defined that for every 2 points in the set, when you draw a line between those 2 points, and these, by the way, the set does not necessarily need to be in a 2-dimensional set. It can be multi-dimensional set. So in this slide, we have drawn 2-dimensional set. It can be 3-dimensional sets, such as a ball. So assume we have a multi-dimensional set. For every 2 points that you choose in the set, when you draw a line between these 2 points, all the points on the line should lie or should be in the set. Then that set is a convex set. In simple words, a convex set is a bumpy set. So it doesn't have any it doesn't have some deviation such as this. And if we have that, we can find 2 points. When we connect them, a part of this line is not within this set. So this is not a convex set. And what is convex hull? When you when you have a set which is not necessarily a convex set, then you can draw the smallest convex set containing that set. Then this set will be a convex hull for this set. In other words, you are trying to convexify the set. Of course, so if I ask you a question, assume you have a set which is convex. You have a convex set. Can someone tell me what is the convex hull of that set? So you have a set which is already convex. What is the convex hull of that set? Anyone?
Would that just be the set?
Yes, exactly. Correct. So thank you. So it means that when you have a set which is already convex, such as this is a convex set, right? The smallest set which contains that set and is convex is the set itself. So the convex hull of the convex set is the set itself. But if the set is not convex, then the convex hull of that set will contain that set, but it will be a bit bigger than that, and it will be convex. So is it clear now, Bansari?
Ben, can you explain it again, please?
Yeah. So using a figure, I think it will be easier to understand.
Yeah.
Assume you have this. Do you agree that this is not convex? Right?
Mm-hmm.
Because when you choose these 2 points and you connect them,
Then it will be convex.
no, I'm saying that this is a test for saying that why it's not convex. If you
Okay.
choose these 2 points, you connect them, you see that this line is not completely in this set. Therefore, it's not a convex set, right?
Okay, got it.
Now, assume I put, I think the easiest thing to understand is that you put a rubber, you know what I mean by rubber? A rubber around it. You put,
Mhm.
or you put a balloon skin around it, okay? And the balloon should be the smallest balloon. The balloon will stick to this part, the balloon will stick to this part, but the balloon will be like this, right?
Yeah.
It won't go inside. The balloon, the smallest balloon containing this set is the convex hull of this set. Why? Now, as you can see, this balloon or this convex hull is convex because you can't find any 2 points within this set which are not where the line between those fall outside of the convex hull. You get it now?
Yeah. So convex hull is something which contains the convex set, right?
Which contains the set.
Yeah.
The set might be convex or might not.
Might
right?
not be. Okay.
Yeah.
So
And yes.
I'm sorry. So can we say like the whole is just like the
Perimeter or the boundary?
yeah, like the line segment is like the longest line segment. It's not
The longest what? Sorry, what?
sorry. So like the longest line segment that's not contained inside. Like
It will contain the set definitely. So the set is a subset of the convex hull of the set. You agree with me? So this set is within this set, right?
oh okay.
That's why I'm saying that the set is a subset.
So the convex hull is like the smallest one, right? So it's like so then like the rubber have to be like a straight line, right? Or does it have to be?
Does it have to be what? I couldn't hear you completely.
Like a straight line, like
No, it's not necessarily a straight line, but first off, when you say line, you are thinking only in 2D, because if it is a 3D, then that part is not a line; it will be a hyperplane. It will be plane. If it is in 4D, it will be hyperplane, right? So this is one thing that you should note. And in this particular case, yes, when we have a non-convex part of this set, I think yes, maybe you can look at this part locally, and it will be something like a line or hyperplane. But in these parts, then it won't be a line anymore because it will have some deviation. You get my point?
yeah. So
Yeah.
would the rubber be just like the largest
Not largest, the smallest. The smallest convex set containing that set.
Yeah.
Yes. Okay. Everything clear now?
Yeah.
Okay, great. And why is it important? Because sometimes we have a set which is not convex and we want to convexify it. So that's one thing. And another thing, but before I continue, I wanted to introduce your TA. So your TA is Mr. Shafahat Ali. I write it in the chat, and his email I also write it in the chat for you to know. I will mention that in the course link too. And by the way, before we go to the course, did everyone get added to the Teams group that we have?
I got an invitation.
Yes. So
Yes, Ben, we were added.
So yes,
Was
and
added.
could everyone please check whether you see a channel named question answering within that group? And if anyone is not in the added to the Teams group of the course, please let me know. You can also send me an email and I will add you. So please let me know. I need to know that. And if at least one of you, please kindly check whether you see there is whether you
there's a
see
channel named question answering.
answering.
Yeah,
So
I
you
see
can
that.
see that. Okay, that's great.
Yeah.
So and yeah, yes, okay. Milad, you said you haven't been added. Could you please send me an email because I might lose the chat here after the class. Therefore, I appreciate it if you please send me an email. Anybody who's like Milad is not added to the group, Teams group, please kindly send me an email and I will definitely add you. Okay, so and please, anyone, if you have any question off class question or discussion, feel free to write in the question answering channel and I will answer. I or TA will answer. Also, please answer each other. So you can answer each other and it will be I will be very happy if you answer each other and participate in the discussions. Thank you very much. So one thing that okay, now let's go maybe to the course. So share screen. Something that I wanted to say before continuing the last session, there was something, a formula which I mentioned with hesitation. Now I want to say it more precisely. Do you remember interior? I said, look at the figure. But then after class, I thought more about the formula. Now I can say it with clearer explanation. So what this means is this: there exists at least an epsilon, which is greater than 0. It means that we have a positive epsilon, which usually we show small numbers by epsilon. And what is this? This is the set of the neighborhood of X. So for a point, see, a point X in the domain, in the set D, the interior, this point is the interior point of this set if the neighborhood, this is the neighborhood of X lies within the set D, is a subset of D. How? And why is it neighborhood? First off, why is it neighborhood? It means that the set of points Y, where, this means which or where, the distance, this is a Euclidean distance. This is L2 norm of Y minus X. These are two vectors. And this exactly means summation of elements. If, for example, it's d-dimensional, if it's d-dimensional, this means summation of elements yi minus xi. It has a square root. So this is Euclidean distance, right? So it means that the Euclidean distance of y minus x, or of y and x, is less than or equal to epsilon. It means that this is x, this is a neighborhood around it with radius epsilon, and this is this set. And y lies, y is all of the points, this set is all of the points of y which are within this neighborhood, right? And this means that this set neighborhood is within the set D, and this is D, assume D. So this point is a interior point of D because its neighborhood is within D. And now let's look at the edge cases where D is on the boundary of D. Is it an interior point? No. Why? Because its neighborhood, some of its neighborhood, I mean this part, is not inside D. Therefore, the boundary is not the interior. Also, if the point is outside D, like this, its neighborhood is not inside D. All of its neighborhood, if all of its neighborhood for a small, sufficiently small epsilon if it is in D, then that point will be an interior point. And this is a definition of our interior point. And if we have a collection or a set of all of the interior points, then we'll have the interior set. And this is the interior set. So all of the interior points of a set D is the interior set of the D. So is it clear now? This is slide. Yeah.
Ben, one question.
Yes.
What's the 2 around the Euclidean distance? Y minus x, then the 2.
Which these two?
Yeah.
This is L2 norm. I will introduce the norms in this session. So
Okay.
if we have, for example, this is LP norm. P can be 1, 2, it can be numbers.
Okay.
I will introduce it in this session. So
Okay,
we'll see that. When it is 2, so when we have x minus y or y minus x 2, this is equivalent to Euclidean distance.
Okay.
And Euclidean distance means exactly the length of the line connecting these two vectors. So if you have, this is a vector, this is a point, right? This is a point in the space. This is another point in the space. If you connect a line between these 2 points and you measure the length of this line, this will be the Euclidean distance between x and y. And the L2 norm of x minus y is equivalent to the Euclidean distance of points x and y. Okay.
Thanks.
So and I will introduce the norms very soon.
Got it.
Okay.
Another
yes.
Sorry,
Sure.
is P related to the dimensionality of a set then?
No. So don't confuse several things. Set is a set of points within the space, right? And X is a point, and every point is a vector. Do you agree with me on that or not? So when we have a d-dimensional space, so assume we have x1, x2 until xd, right? It means we have d dimensions. Okay. Every point in this space, let's call it x. I mean bold x, which is a vector, right? Every point in this space is a vector. Why? Because you can connect the origin to this vector. Therefore, every point in this space is a vector. What was your question again? So we can have a set of points. So don't confuse these concepts. And you said your question was about P, right? P is in a definition of the norm, which I will introduce. It's not necessarily related. No, it's not related to the dimensionality of data. And the dimensionality of data is the number of these axes in the space. So when you have two-dimensional data, it means that it's a plane. It's like your monitor. And if it is one-dimensional, it's a line. If it's two-dimensional, the space is the plane. If it's three-dimensional, the space, you can consider it as a cube which goes to infinity. And you can have four-dimensional or d-dimensional. Do you get it?
Yep, makes sense to me.
Yeah. And P is not related to dimensionality. We'll go over that. Okay. Again, if anyone has any question, please let me know. There was one more thing in the last session. It was here. If you remember, I said the inner product is the projection, the length of projection. But you should note that when we have someone is not mute. Yeah. Okay. So I said when we have inner product is related to it's the length of the inner the projection, but that's true when the vectors are normalized to have length 1. When in general case it's this. So when we project a vector y on vector x, we'll have vector z, right? This is projection because it's perpendicular, and this z can be represented as y transpose x over x transpose x times x. So the length of this set, the length of this projection is y transpose x over x transpose x. If, and what is this? This, you can write x transpose x as second norm of x squared. We will talk about this. And this is the normalized x. It means that its length is 1. If that's the case, then as you see, the length of the projection would be y transpose x. So you should note that this explanation is just for the relation of projection and inner product. Again, you can project x onto y. If you do that, then this vector k will be more than y, and it will be k x transpose y over y transpose y times y, and this is the length of k. Did someone ask any question? No? Okay. And so this is one thing that I wanted to correct. And another thing is that you should note that x transpose y is always equivalent to y transpose x. So the order doesn't matter. So it means that why? Because it's this proof is very simple. X transpose y is x1, y1 plus x2, y2 until xd, yd, right? And y transpose x, y1, x1 plus y2, x2 plus yd, xd. And the order doesn't matter in multiplication. Therefore, these are equivalent. So the order doesn't matter in inner product. So far, everything clear? Yeah, okay. What is norm? We want to define norm. A function, we usually show norm by this. So we have two lines here, something in the middle, and two lines there afterwards. It goes from RD, d-dimensional Euclidean space. So its domain is d-dimensional Euclidean space. And its output is always a scalar. It's a scalar. So it gets a vector and it outputs a scalar. We have some norms which get matrix. So it gets either a matrix or a vector, and its output is always a scalar. And the norm of x is shown by this. It's a norm. It should satisfy 4 conditions. First off, the norm of x is larger than or equal to 0 for all x. So it's non-negative. The output of norm can't be negative. That's one important thing. Also, when you multiply the argument of this norm by some scalar a, you can bring the scalar out of the norm, but you need to have an absolute value. Why? Because this norm is always non-negative. You can't have this. If a is negative, you should take an absolute value. Another thing is that if x input of the norm is 0, a 0 vector, the norm will be 0. And vice versa. If the norm is 0, its input must be 0. Because it's if and only if. It means if x is 0, the norm of x is 0. If norm of x is 0, then x is 0. So both, it's two-sided. And triangle inequality. It means that norm of x plus y, these are two vectors, the norm of x plus y is always less than the norm of x plus norm of y. And this is very important thing in, so what, for example, something like this, it's similar to this case. You want to go from here to here. What is, why do we call it triangle inequality? Because of this. You want to go from A to B, but there is a point C too. Assume you put a donkey here. And that there is some food here. The donkey can go either in this way or in this way towards the food. Then what the path would the donkey choose? Can someone answer me?
Hopefully just A to B.
A to B. Yeah, why? Because donkey will think about the pass, the length of the pass, and will say that, okay, of course, A to B is shorter than going from A to C and then C to B. That's why it's called triangle inequality, because this length is shorter than the summation of this length and this length. And that's why in either Persian or in Arabic, this triangle inequality is called qaziyatul himar, which means the principle of donkey, because the donkey also chooses this path. And that's an interesting thing. Okay, hopefully with this example, you completely understand what triangle inequality means. Okay, now let's go to the next slide. So what is LP norm? So when we have a vector x, which is d-dimensional, from x1 to xd, and this transpose means that it's a column vector, the LP norm is defined as this. When I say this, by the way, it means the definition. Okay, so the LP norm of x is this. It means that absolute value of x1 to the power of p plus until absolute value of xd to the power of p. Then you take the whole thing, which is the summation of these, and you have the power of 1 over p. So this is exactly this. This is equivalent to this. You know, yes, it is another way to represent this expression, right? So you have root, the pth root of this. So this, I think, answers your question. Who asked the question of what LP norm is? This is LP norm, right? And P has condition is always greater than or equal to 1, and it is usually an integer for us, but it can be floats too. It can be a float number or real number, I mean. And this is absolute value. Okay, so we have two well-known LP norms, which are L1 norm. These are the most famous norms, and L2 norm. And the L2 norm is also called Euclidean norm. So when we set P1 to 1, we'll have L1 norm, and this is L2 norm. For L1 norm, so we don't have this root anymore, because the first root is itself. So the root goes away, and we'll have the summation of absolute values, and these are powers of 1. So we'll have the summation of absolute values. This is L1 norm. So as you see, there is a very similar relation of L1 norm and the absolute value. If D is 1, if we are in one-dimensional space, the absolute value function is exactly L1 norm, right? If D is 1. L2 norm is this, and we'll have the second root of x1d to the 2 plus until xd to the 2. And you have the square root of xi2. Now I think this is L2 norm. And what does this mean? This means that in the d-dimensional space, x1, x2 until xd, if we have a point x, and so this will represent a vector connecting origin, this is origin, to the vector. The length of this vector will be the L2 norm of x. I think it's obvious, right? Because this is exactly the length of the vector x, the definition of length of the vector. And you can also see this in this way. So this or this, you can see this in this way. This is the L2 norm of x minus 0. And now this reminds you of what I said minutes ago. Do you remember? I said x minus y is the Euclidean distance between x and y, vectors x and y. And if you set y to 0, you will have this. So it means that the distance of vector x and origin. So it is equivalent to the length of the vector x itself. Everything is clear so far? Did you completely understand L1 norm and L2 norm? Can someone give me a feedback? Yes?
Yes.
Yeah. Okay, great. So L2, you can use L2 norm in order to measure Euclidean distances. And why do we call it Euclidean distance? Because Euclidean in Greece was the first person who thought that, okay, if we have 2 points on the ground, and we want to see the length of the shortest path between these 2 points, is if we draw a line between these 2 points and we measure the length. So measuring the length of the vector connecting these 2 points together is the shortest path between these 2 points. This is what Euclidean said in ancient Greece. Sorry. So this is what we have for Euclidean distance. That's why it's also called Euclidean norm. And as you see, L1 norm has these absolute values at here in the one-dimensional, for example. You see that absolute value here is not a smooth, right? It's not, it doesn't have derivative here. Therefore, L1 norm is not a smooth. But L2 norm is a smooth. This is one important difference between L1 norm and L1 and 2 norm. So this is not a smooth. Okay, what is L infinity norm? Infinity norm, or it's also called maximum norm or Chebyshev norm. And that's the definition of this. So you sum the absolute values of elements or components of the X, and you take, sorry, I think you shouldn't take max. So you consider the absolute values of these, and you take the maximum. So the maximum element, regardless of the sign. I will correct that in the slides. This is the Chebyshev norm or infinity norm. Some important norms for matrices. So in previous slide, we saw for vectors. Now we see here for matrices. Consider a matrix X in this space. And in previous session, I said this means a matrix with D1 rows and D2 columns. Does anyone know why we can show this matrix with this notation in mathematics? I want you to understand why we are writing this way, because when you understand, you see it's so beautiful. Can anyone explain to me why we can write it in this way? Any ideas?
Because it's always a combination of real numbers.
It's kind of, what you said is kind of correct, but let me restate it. So you can consider this from this side, so this D1 rows as one D1 dimensional Euclidean space. You can consider this from this side. So if you look at it from this side, D1 dimensional Euclidean space, R D1. If you look at it from this side, you will see a Euclidean space with D2 dimensions, right? D2 dimensions. From this side, it was D1 dimensions. Now, so you have two Euclidean spaces. One of them is D1, one of them is D2. Now you have an outer product. This is outer product. Don't worry about outer product, but I can say that it combines these two spaces into a new space, which is RD1, D2. It means that it's a matrix with D1 rows and D2 columns. You can have tensors. You can go, so as you see matrix, you can show it in two dimensions, rows and columns. You can have rows, columns, and heights or something like that. You can go to three. In other words, you can have a 3 tensor. You can have this. So we have D1 rows, D2 columns, and D3. So you will have a cube rather than something like this, you will have a third thing too on top of it. So that's the reason why we can represent it in this way. And this, but simply, you don't need to get confused. It means that a matrix with D1 rows and D2 columns. So what is Frobenius norm? You will hear these a lot in different works, either in papers or in industry. So Frobenius norm is similar to L2 norm for vector. Do you remember what was L2 norm for vector? It was second root of x1 squared plus xd squared, right? But in matrix, we have both rows and columns. So xij means the ith row and jth column of x. You square it, and you sum over all rows and columns. And then you take the second root. So this is a Frobenius norm. As you see, it's very similar to the L2 norm, but this is for matrices. Note, we also have L2 norm for matrices with another definition. This is out of the scope of this course. Why do I say this? This is not L2 norm of matrix X. It's not L2 norm. This is Frobenius norm. So don't confuse that. I just wanted to mention this. So far clear? Please, if anything is not clear, let me know.
So is Frobenius norm just L2 norm?
No. Frobenius norm is similar to the form. Frobenius norm for matrix X is similar to the format of the L2 norm for vector X. See, Frobenius norm of this similar to L2 norm for vector X, right? Do you see the similarity between these two? So this equation, L2 norm, this is L2 norm. Look at the L2 norm. You have only the dimensions 1 to D, right?
Yeah.
You only have, but in matrix, you have dimensions 1 to D1, also dimensions 1 to D2, because you have both rows and columns. Except this difference, everything is similar between Frobenius norm and L2 norm. I go back and forth so you can look at it. Do you see that?
Yeah.
So that's what I said. So Frobenius norm for matrix is similar to the L2 norm for vector X. But we have some L2 norm for matrix, which I'm not introducing. It's out of the scope of this course. Don't confuse it. Okay? So far clear? What I mean by this, I mean this.
About I and J.
I and J here. So what I meant is this. And I and J. I and J mean I is on rows. J is on columns. This is summation on rows and some. So let me, I think, in order for you to understand, let me explain with an example. Assume X is 1, 2, 3, 4. Okay, maybe let me make it 5, 6. Okay, do you agree this belongs to R2 by 3? It has 2 rows, 3 columns, right? Is that correct?
Yes.
Okay. Now, what is the Frobenius norm of X? Second root of 1 squared plus 2 squared plus 5 squared plus 3 squared plus 4 squared plus 6 squared. This is Frobenius norm. So element-wise, I squared them, then I sum them, then I take the second root. Clear?
Okay.
Now, assume you have a vector now, 1, 3 only. This is a 2-dimensional vector. Do you also understand this notation? This means a vector with 2 rows only, right? Do you also understand this notation?
Yes.
Okay. And what is the L2 norm of this? Please you tell me. I want to write.
1 square plus 3 square.
Exactly. Exactly. What is the L1 norm of this? Can you say that? Can you say that?
Mm,
Do you remember? So this is the equation. Please look at it and let me know the answer. So this is L1 norm. Please look at the L1 norm. The summation of what? Absolute values of elements, right? Is that right?
yes.
Okay. So now what is the L1 norm of this vector?
1 plus 3.
Exactly. So assume 3 was minus here. Also here was minus. Do you agree with me that all of these Frobenius norm, L2 norm, L1 norm were the same? Because recall that in all of them, for every element, you take the absolute value. See here, I can show you. In L1 norm, for elements, for each element, you take absolute value. For L2 norm, you already square it. So square also takes absolute value, doesn't matter. Minus 3 squared is equivalent to 3 squared, right?
Yes.
You can also look at the definition of LP norm above here. You can see that also we have absolute value of elements. You might be wondering why I haven't put absolute value in. Sorry. Just give me a second. You might be wondering. My tablet had some problems. Just give me a sec. I can fix it. Just give me a sec. Okay, I'll fix that. So you might be wondering why I haven't put absolute value for here. Because x1 absolute value squared is equivalent to x1 squared. You don't need to take absolute value for a square, right? When the power is even, an even number. So this is another thing that is it clear now what L1 norm, L2 norm mean? And Frobenius norm? Is it clear to everyone? Right?
Yeah.
Yes.
Okay. Okay,
Yeah.
great. Now we know norms, which are very important. Very
Sorry.
important. Sorry. Okay.
Is there a geometric interpretation for a matrix norm?
For a matrix form, yes, I think it is. So let me think about it a bit. So assume we are in a space of assume we are in the space of this RD1 outer product D2, and this is a space which I can't visualize. I can imagine. So the space of which is the outer product of two Euclidean spaces, one of which is D1 dimensional, the other one is D2 dimensional. So we have a space, a Euclidean space by the outer product of these two spaces. And then in this new space, Euclidean space, I have a point. And this every point is a matrix. So if I change the elements of this matrix, I will have different points in this Euclidean space. And the length of vector connecting origin of this space to every point is the Frobenius norm of the point. Do you get my point now? Do you understand what I'm saying?
Yeah.
Is that clear? Yeah. So this is the interpretation. As you see, Frobenius norm, L2 norm, these norms, and in other words, these norms are, so take a look at LP norm, also similarly for matrices and all of these. When we say LP norm, it's a kind of distance metric. Why? Because this definition of distance also includes these things. So you can see a close connection between distance metric and norm. You can see that this is the definition of norm. You can look at the definition of distance metric and you will see that also has these conditions. And so there is a connection. That's why when we say the norm of a vector, we are kind of referring to the its length or its distance from origin. And when we say the norm of x minus y, the norm of difference of two vectors, we are saying that this is the distance of x from y. And you might, if it is L2 norm, this is what we learned in high school. This is the length of the vector, the shortest path connecting these 2 points, or the point to origin. But when we have LP norm, we'll have other distance matrix. So in other words, let me show it here. So you have 2 points. This is length of this is a distance metric. Length of this might be also no, not this. But if the space is curved, something like that, then the length of these two, this might be a distance. So you have different definitions of distance. It's not just the high school definition of distance. LP norm, by changing P, you will have different types of distance between the points. And if you have only X, it means that the distance of X from origin, or the length of X. If you have norm of X minus Y, it means the distance between X and Y. Do you get my point? Everything clear?
Yeah.
Yeah, okay. And did that answer that question? Okay. Yeah. Okay. And these are two important equations that you should know, that L2 norm, a squared L2 norm of X is equivalent to this, X transpose X. Why? I can show you the proof. Assume X1 is 1 minus 3, okay? What is L2 norm? It's 1 squared plus 3 squared. What is its, when we square it, it is 1 squared plus 3 squared. Now, what is X transpose X? This is 1 minus 3. And this is 1 minus 3. This is X transpose, and this is X. So now you multiply these two vectors or matrices. 1 squared plus 3 squared. As you see, these two are equivalent. You can write it in, if for general case, when we have d dimensions, right? You can write it for d dimensions. So as you see, these two are equivalent to this summation of x1 squared plus x2 squared and all of this. And when you have Frobenius norm, you can write it in this way. So trace of, I defined trace in the last session. Trace, you can see it as a summation of diagonal elements of X transpose. So here, this is the summation of diagonal elements of X transpose X. Again, here. When you have a Frobenius norm squared, so do you remember the Frobenius norm? You just need to square it. So you'll get rid of this second root, this second root. So these two equations, you can use these interchangeably. And as you see, these two are both quadratic. When you say quadratic, it means squared. So you see these squared. They are squared. You can also see these squares here. And these are convex and quadratic. And their shape is like this. Assume in 2 dimensions, if, for example, you have these two, you can say x1, x2 are the inputs, and the function, assume the function is this, x1 squared plus x2 squared. This is exactly the function is, this is the function this, which is x1 squared plus x2 squared. And you can see it's like a bowl coming up. You can look at it from above and you will see this. And these lines means that on each line, the function value is the same. So the bowl is coming up, the bowl is coming up, right? Okay, so you can see this is quadratic, these are quadratic forms. If anything is unclear, please let me know. And what is unit ball? First off, you should note that there is a difference between ball and a sphere in mathematics. When you say sphere, you are referring to its surface. When you say ball, you are considering both surface and inside the surface. So ball is like the whole thing, including it inside of it, it's in interior, but the surface is only its boundary. This is an important difference between ball and surface, especially in mathematics, in topology and all of those areas. So, and what is ball? Ball means all of the points in D-dimensional space where their norm is less than or equal to 1. For example, assume you have 3-dimensional space, x1, x2, x3. This is the ball with radius 1, where inside of it is also in it. So this is a ball. But for different P, for different LP norms, this is a ball in 3D for L2 norm. For different LP norms, for P, different Ps, we have different shapes of ball. And that's an interesting thing. For example, these are all in R2. But this was in R3. In R2, if it is L1 norm, the shape will be like this. If it is L2 norm, the shape will be like this round. If it is L infinity norm or Chebyshev norm, the ball will be like this. And I think it's obvious why this is happening. For example, what was, it was max of x1 until xp. So, for example, when we are here, when we are in this line, here, x1 is can be 1, but we can't have any other elements more than 1. Why? Because this condition will not be satisfied. If here x1 is 1 and x2 is more than 1, then the length of the x will not be less than or equal to 1. So we will saturate here. And if we are here, we will saturate here. If we are here, we'll saturate in x1 equals -1 because x2 can't go further. Otherwise, this inequality will not be satisfied. Also here, you can have the same conditions for this. For example, when you have L2 norm, this is radius 1, right? You can't go more than radius 1 because this condition will not be satisfied. You can go inside of it. So this also contains inside of it. It's ball, it's not a surface, right? It's not a sphere. It's not a circle. It's ball, it contains its side. So it contains its side. It contains its side. You have also a L1 norm. An important thing that you can see in both Chebyshev and L1 norm is that they are not as smooth. Here, 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 here. They are not as smooth. Here, 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 here. They are not as smooth. But L2 norm is very smooth. You can see that here for L2 norm, everywhere you can define derivative. It's completely smooth. There is no corner. But here you have corners. L1 norm, Chebyshev norm, these have corners. They are not smooth. Therefore, working with L1 norm, Chebyshev norm, and these norms which are not smooth is harder than working with smooth norms like L2 norm. Frobenius norm is also a smooth norm. Its behavior is similar to the L2 norm. So this is another thing that you should note. Clear everything? Okay. We have a concept for dual norm. And dual norm, it's a mathematical definition. Again, this means define. We usually denote dual norm with a star here. So this is a dual norm of X. And this supremum, do you remember? We define supremum. You can see it as a maximum, but maximum is a special case of supremum because supremum also considers the case where the function goes to a point but never reaches that, right? And so this is, consider a set X transpose Y. X is the argument of the dual norm, and Y has a condition on it, where the norm of Y is less than or equal to 1. So this is norm. This is the dual for that norm. As you see, the definition of dual norm, of course, contains the norm itself, because this is a dual norm for this norm. This is the mathematical expression. We will see some examples for dual norm in the next things. By the way, you should also note that when we say this in the literature, it may have two meanings. It's either dual norm or it's nuclear norm. Nuclear norm is related to singular values and all of these. I haven't defined that in this course. It's out of the scope of this course. If you are interested, you can search it later or ask me off class. But I'm saying, why do I say that? Because so you don't confuse this. Sometimes it might be dual norm, sometimes it might be nuclear norm. We haven't introduced nuclear norm here in this course. Okay. Again, I will show you some examples of dual norm, but please be patient a bit for that. So we have Holder's inequality. And what is it? It means this. This is Holder's inequality. It means that the absolute value of X transpose Y, do you remember? This is definitely a scalar. Because if you remember when I was introducing the inner product, I said the inner product output is always a scalar. The absolute value of X transpose Y is less than or equal to norm of LP norm of X times LQ norm of X, where the P and Q satisfy this equation. So 1 over P plus 1 over Q is always 1. We'll see some examples. For example, if you set P to 1, Q will be 1. Q will be infinite in this equation. If you set Y, because 1 over 1 will be 1, 1 over infinite will be 0, 1 plus 0 will be 1. If you set P to 2, Q will be 2, because 1 over 2 plus 1 over 2 will be 1, right? If you set P to infinite, Q will be 1, because 1 over infinite is 0, plus 1 over 1 is 1, right? And PQ is more greater than or equal to 1. This is the Holder's inequality. A special case, I think many of you have heard in other courses maybe, is the Cauchy-Schwarz inequality. This is the most famous inequality in mathematics. It shows off in many areas of mathematics, and it says that when you set P and Q to 2, you will have Cauchy-Schwarz inequality. Okay, so its interpretation, geometrical interpretation, is that when you take the inner product of X and Y, which is related to projection of X onto Y, do you remember? I said this. The length of projection of X onto Y, if we normalize the two vectors, this is the length of the projection. And why do we take the absolute value? Because the inner product's output might be negative. So we take absolute value. And then say that this is the length of X, This is the length of Y. this must be y. Sorry, I will correct that in the slides. And in several minutes ago, I mentioned why this is the length of x, right? We showed that. So length of x times length of y is greater than or equal to the length of their projection onto each other. And simply, if you put this in this equation, you will have this. You can say when you have LP norm, it's dual. So just give me a second. So yeah, I think exactly. P and Q here, I should tell you that LP and LQ are dual norm of each other, dual of each other. Here, do you remember I defined a dual norm? And LP and LQ norm, if they satisfy this equation to this, then they will be dual of each other. Therefore, you can see that the dual of LP norm is always P over P minus 1. Why? Proof is so simple. 1 over P is 1 minus 1 over Q. Q minus 1. And if you simplify this equation, you will get to this. So from this, you can simplify and you will see that Q equals P over P minus 1. From this equation 2, we can see that the dual norm of L2 norm is L2. The dual norm of L1 norm is L infinity. The dual norm of L infinity is L1 norm. I'll show you the examples here. I said I will show you some examples. This is L1 norm. The dual of it will be like this, which will be L. This is L infinity norm. This is L1 norm. The dual norm of this will be on it itself again, L2 norm. The dual norm of this will be this. This is L1 norm. This is L infinity norm. So you can see that also visually, you can see that dual of L infinite norm is L1 norm. Dual of L2 norm is itself. Now cone. Let's define cone. A set K is a cone. If it contains origin, it must contain the origin. This is important. If it's a convex set, and if for any lambda which is greater than or equal to 0, a scalar lambda, if a point for each point in the cone, lambda x is also within the cone. And what does this mean? Assume this is a cone. This is an example cone. This is an example cone. Cone is exactly similar, its shape is to the cone of the ice cream, right? But it might have different angles. So this is angle alpha. It might have different angles. So it definitely contains the origin here. If there is a point x here, if the line connecting origin to this, if you multiply it to anything by lambda, the point lambda x also will be inside the cone. As you see, obviously, visually, you can see that when the point is inside the cone, when you connect the line from origin to that and you multiply it by lambda, you will see that it still remains in the cone. In other words, it means that this condition 3 means that it goes to infinity somehow. And it is also convex. You can't find any 2 points in this set where the line connecting them doesn't lie within that set. Everything clear so far?
What is convex set?
Convex set, we defined that in previous session also. So when we have a set, if we have 2 points, the line connecting them should completely be inside the set. Otherwise, it won't be convex. Do you remember this? This slide. Let me bring it. here in this slide. Do you remember? Slide 11. We said that the convex set is kind of a set which is bumpy. You can't find any 2 points where you connect the 2 lines to each other. All the lines should always be inside the set. Like, for example, this is a non-convex set. This is a convex set, right? Because you can find 2 points here where the line connecting them, some of it is outside of the set. Clear?
Yes, okay.
And why is the cone convex? Let me bring it. Why is the cone convex? This is a cone, right?
It's like
contain-
circular.
What?
It's
Sorry,
like
what?
circles.
It's like what?
It's like a bunch of circles.
This it's not a bunch of circles. No, this is a cone. You can see this is, so in 2D this is a cone. In 3D, for example, how can I show the 3D cone?
Well,
This is a
like
Yeah,
it's
like the
convex
iPhone
because
phone.
any point connected to the origin will never go outside the set.
yeah, but I don't understand why you bring origin here, because any 2 points like X and Y here inside this set, the line connecting them is inside the cone. Is it obvious? When we
Yeah.
are saying that the set is convex, it means for any 2 points. The point might be origin, because origin is also in cone. Or any 2 points, not necessarily the origin. So, and in 3D, this is a 3D cone, right? And the dual cone is this. If we have, this is a cone. The dual cone, I show it. So perpendicular to this one, I'll also draw this perpendicular to this side. So to each of the sides, I draw a perpendicular side. So if this was a cone K, this whole thing is the dual of cone K. Is it obvious? It's exactly this shape here, shown here in this. So this is the cone K, and this whole thing is the dual of cone. So these are some concepts, because as a preliminaries, you will see a lot of these concepts in the literature, and you should know what these mean. And this is a two-sided cone, two-sided cone. So you can have, so again, see, it satisfies all the conditions of a cone. If it is X, lambda X also is inside of it. Also, it's convex, and it also has the origin. So it's two-sided cone. But if you have one-sided cone, then it's called proper cone. It should be closed, should be solid. It shouldn't contain any line. So it doesn't have any line in it. Why? Because this is not a line. Line goes from infinity to infinity and passes through origin. So this part of the line is not inside the cone. Therefore, in other words, this is a one-sided cone, and this is a proper cone. So when you see the term proper cone, it means this is a one-sided cone. Okay, generalized inequality. That's an important concept. A generalized inequality defined is this. So when we say this, what does it mean? It means that if you bring y from this side to this side, so for example, in algebra, when you say x greater than y, what does it mean? X minus y is greater than 0, right? In simple high school when we said that. Do you remember? Now we can say generalize. We can generalize. We have generalized inequality where we say that it has an index, a subscript k, which means the cone k. You can also have the same thing. Bring y to the other side, and this will be this exactly here. What I draw here. And what does it mean? What does it mean? It has an interesting fact. It means that if you have x in the cone here, and also here, if you have y in the cone, the vector connecting y to x should be inside the cone. If the vector connecting y to x is inside the cone, then this inequality is satisfied. Then you bring y to the other side, then you will have this. It means that with respect to the cone k, x is greater than y. Do you see that? Here, x is greater than y. Now, we go to some interesting things, and you'll see whatever you knew as the inequality in your head is a special case of this generalized inequality. When we say this, it means by default, we means the cone is the positive orthant. And what is a non-negative orthant? It means that, for example, if in 2D, it's here only. When all the axes are non-negative. So this means this in D-dimensional, all the D axes are non-negative. And it means that this particularly means that all elements of X, every element of X is greater than or equal to every element of Y, element-wise. So for example, an example. X is 1, 3. Y is 0, 1, 0, 2. X is greater, so we draw it with this way. It has some deviation in the inequality because these are vectors. These are not numbers anymore. These are not scalars. If they were a scalar, we could simply say like this. But when they are vectors, we have some deviation in the notation, like this. This means that the first element of X is greater than or equal to the first element of Y, which is 0 here. The second element of X is greater than or equal to the second element of Y. Element-wise, X is greater than or equal to Y. This is what it means. Again, element-wise, right? When we have matrices, the default is for positive semi-definite cone. And simply it means that when we have this, it means that X minus Y is greater than or equal to 0. And this means that this matrix X minus Y, this is also a matrix, is positive semi-definite. If you don't know what positive semi-definite means, don't worry about it. These are just introduction. I want you to understand these concepts. Otherwise, I won't bring these in the exam. So don't worry about that. I would just want you to learn and have fun understanding what these mean. Positive semi-definite means that the eigenvalues of X minus Y here are non-negative. They are either 0 or positive. And the eigenvalues and eigenvectors, you can search it off later, off class, but you can see that eigenvalues show the import. So when you have, usually when you have a matrix, you can find its important, it shows some important directions. Those important directions usually are called eigenvectors. And the length of those important directions are called eigenvalues. You can read it offline. But if the eigenvalues are not, all of them are non-negative, then it's called positive semi-definite. And this means that X minus Y is all of its eigenvalues are non-negative. So this is generalized inequality. Now you can see what we had. We had inequality for scalars. We had this, right? For if X and Y were a scalar. But now if they are bold, if they are vectors, or if they are matrices, we also can define inequality between them. Inequality between vectors, inequality between matrices. This slide is showing how this can work, how we can have inequality. So for vectors, it's element-wise comparison. For matrices, it's related to eigenvalues. Okay, so preliminaries on sets is over now. Now we go to some important thing about functions. So I think it's good to have a break here, if you agree, and we come back at maybe 8:35. Does everybody agree with that?
Yep, sounds good.
Okay,
Sure.
great. Okay, sure. At 8:35, I'll see you. Thank you. So I just wanted to let you know that you might think that it's getting a bit theoretical. These parts are necessary for you to understand what these concepts are. For me, it's not important whether I don't want it to be theoretical much. The reason that I'm explaining this to you is to understand the concepts. And please note that I won't examine you on the theory. These hard theories. I want you to be introduced to these concepts, and your exam will not be very hard. I will make sure to make the exam similar to the assignments. So also, we don't need to worry about that. Please also say this to the other classmates who aren't present right now, so they know that the exam will not be very hard. Because the reason for the course, I think, is not to suffer students or suffer anyone. I don't want to be suffered. I don't want to suffer you. The only thing that I want is that we learn optimization together, and we just have fun understanding the algorithms, the concepts, and these things. So from my side, don't worry about the exam and all of these things. The exams will be simple and similar to the assignments. So the only thing why I'm saying this, because I want you to completely release the stress, anything, and don't think of, oh my God, how I can have all of this theory in my mind. I don't want you to do that. The only reason that I'm saying this theory for you to understand the concepts and see how fun and cool the concepts of optimization are, and it will get easier. I think these concepts were a bit theoretical and scary, but I think it will get easier. And the more we go, the more you will see it's so simple and interesting. Yeah. And please don't, because I used to be student too. I know the stress of exams and these things. Please don't be stressed at all. At all. I will not make the exam hard. Just give me a second, please. Okay. So now, without any stress, try to listen, understand, and with peace of mind. And also, please be in the discussions. Challenge me, or let's understand something. If you don't understand a part, shout it and say, okay, I didn't get it. Can you repeat? And so we go over that. So don't worry about anything. Again, please say this to your friends too, who are not in the class right now. I want everyone to understand that this course is not for stress. This course, and if we even go through the theory, it's not because of you to be examined on those. No, it's because of you to understand why what these concepts are and why these work. So don't worry about that. Again, please say that to your friends who are not present right now too. Okay, and no problem. Okay, thanks. Yeah. Please see me as one of you. I don't want to be suffered too. I won't suffer you. So I am saying that the exam will not be hard. Don't worry about that. So let me share screen. Okay. I think you're seeing that now. Let me. Yeah. Okay. So I think now we are going to preliminaries on functions. What is convex function? So don't confuse convex function with convex set. Do you remember we explained what convex set is? This is convex function. So a function f, assume its domain is D. Domain, what does domain mean? Domain means where we can have the input of the function. So what is the feasible region for the input of the function f? That's called domain of x. I denoted by D. And if we have this, so do you remember this? Alpha x, so assume x and y are in this domain. Okay, for any, this means for all or for any 2 points in this domain. So, and what is this? Alpha x plus 1 minus alpha y. This means that, assume this is x, this is y, that this is the line connecting x to y. So this, if alpha is between 0 and 1, the alpha x plus 1 minus alpha y represents this line. Why? Because if you set alpha to 0, this becomes y. This, if y, because 0x plus 1 y. If you set alpha to 1, this becomes x. So this is for alpha 1, this is for alpha 0, and for alpha between 0 and 1 will be underlined. And this says that f of this for, so if this is x, for example, this is y. So for all points here in this region, which is alpha x plus 1 minus alpha y, any point here, if we feed it to the function f, it will have this. F of this is less than or equal to alpha f of x. So you feed x as input to f. You also have feed y to the f. So we'll have f of y. 1 minus alpha times this. Alpha fx plus. So you kind of have this. Don't confuse the left-hand side with right-hand side. You see the difference, right? And what this means, again, left-hand side means that a point here, you feed it to the function, you will, for example, this point, you feed it to the function, you will get this. So this is f of alpha x plus 1 minus alpha y. What is this? This is f of y, right? This is y. What is this? This is x. So this is f of x, right? So if you multiply this f of x by alpha, multiply f of y by 1 minus alpha, you sum these, you will have this line. You will have this line. This is exactly alpha f of x plus 1 minus alpha f of y. And as you see, f of this, which was this, is always below this line, So this inequality, or this is the definition of convex function. In other words, always the function is bumpy in a way that in this way. For an example, which is a counter example for this, is this. See, for example, for this for these 2 points, this is x, for example. This is y, and let this choose alpha in a way that this becomes f of alpha x plus 1 minus alpha I. And as you see, this doesn't lie below this line. Therefore, this is not a convex function. In simple words, it's always bumpy in this way. This is a convex function. So it's like a bowl. You can see the convex function is like a bowl. This is a one-dimensional function. Why? Because its input is one-dimensional, its output is also one-dimensional. You might have multi-dimensional inputs, right? Then, if, for example, if you have two-dimensional input, it will be a bowl. How? It will be like this. So 2 dimensions, x1, x2, and the third dimension for f, value of f. For example, this function, like a bowl, this is also a convex function, right? So we might have multi-dimensional inputs. The function is always the function here. We are talking about the scalar functions, but the function itself might be also multi-dimensional. Here we are talking about the scalar functions. So as you see here, this is a convex function, and this is obvious what it means. This is a definition of convex function. Alpha is between 0 and 1, right? Because if alpha is less than 0 or greater than 1, will be on these sides of the line. We want to talk about inside. We want to talk about inside. Okay. And if we change this inequality here to greater than or equal to, we'll have a concave function. Concave is the opposite of convex somehow. If this is, how should I draw it? If this is convex, then concave is like this. So you look at it the other way around. So it's bumpy in this way. So this is bumpy in this way. So it's like an opposite bowl, right? This is concave. Now, convex function has multiple definitions in the literature. The previous slide was one of the definitions, the most famous one. This is another one. Or you can say the convex function also satisfies these equations that I'm going to tell you. One of them is this: if the function, convex function, is also differentiable, so you can take derivative. Okay, it means it doesn't have a non-smooth part. It's always a smooth. Okay, then the convex function also satisfies this inequality. And what this means, I have drawn it here. For all x and y in the domain, so any 2 points x and y, take this is f of y, this is f of y, this is f of x. This line is the tangent line on this function. So this is the function, right? This is the function. The tangent line on this function, which is tangent on this f of y, its equation is this: f of y plus derivative of f of y transpose. This is the inner product. So inner product between x minus y and derivative. You remember this was, so take this, transpose this, means the inner product of these two. And it's so obvious, tangent always is related to the derivative. The derivatives, because this is the slope. The derivative is the slope of the tangent, right? That's why this is the equation of this line, and this is f of x. And when you have a line or a hyperplane, you can be on this side of the hyperplane or this line or the other side. If, for example, you are on this side of this line, then f of x is greater than or equal to this line. If it is less than or equal to, it means that we are on this side. In other words, when we have a convex function, this point is always on this side of the line, not this side. A counterexample. Take this y, this as x. The tangent will be like this. F of x is here. This is f of y, and this is the tangent line, which is whose equation is this. f of x is on this side of this line. Therefore, it's not convex. It need all for every 2 point xy, f of x should lie on the other side of this line. In other words, this tangent line should always lie behind or below the function. This tangent, if you move the tangent, so if you move the point y to the left and right, you can see the tangent is always below it. See, I'm moving y and the tangent, imagine the tangent. So this is the tangent, for example, one of the tangents, another tangent, another tangent, another tangent. All of them are below the function. If at some point the tangent goes above the function, it means that the function is not convex. I think it's also, it makes sense. And again, if you change the inequality, the convex becomes concave. We might have a third case where it is neither convex nor concave. We might have the curve. So don't think that the function is always either convex or concave. No, we might have a function, for example, this function is neither convex nor concave. It's a non-convex function. Everything clear so far? Yes? Can you give me feedback? Okay. No one is saying anything.
Yes, it is clear.
Okay, great. So now, and the third definition for the convex function is this. When it is, again, differentiable, when we can take derivative, then this definition is about the second order derivative. So the previous one was about the first order derivative. The second order derivative is always positive semi-definite. Positive semi-definite. And what does it mean? Positive semi-definite means that all its eigenvalues, again, if you don't know what eigenvalues are, please read it offline or ask me off class, because it's a bit out of the scope of this course. But it means that all of its eigenvalues are non-negative for all points x. But geometrically, what does it mean? It means that always its face is toward up. This, when the second derivative is greater than or equal to 0, or this, it means if the do you remember when we said in the high school, when the second derivative of a function is greater than or equal to 0, it means that it's like this. When the second derivative is less than or equal to 0, it means it's like this. It's facing down. It's facing up. So it means that it's always facing up. So a counterexample, an example here, this function on this part is facing up, on this part is facing up, on this part, however, it's facing down. So it's not a convex function. For all x in the domain, it should always face up. So it's also a convex function. Again, if we change this to this, it means that all of its eigenvalues are non-positive. Are either 0 or negative. Then it will be a concave function, right? Okay, what is a strongly convex function? A differentiable function, again, if it is differentiable, is mu strongly convex, mu strongly convex. Do you remember, if we had this term, it would be convex. Then it adds something else to the right-hand side with a parameter mu. That's why it's called mu strongly convex. Where mu is positive. Okay, if mu is 0, then it's convex. But if mu is positive, it's strongly convex. Another definition for this is this. When y transpose this second derivative y is greater than or equal to mu squared L2 normal y. But what is important for me for you to understand is that is its geometrical interpretation. What does it mean? It means that when we say convex, we might have somewhere like this. See, this is still convex, a convex function, where all of these parts are the same. Again, according to all of the definitions that we talked about, for example, this. If you take this line, all of these are under this line. This is a convex function. However, it's not a strongly convex function. A strongly convex function is like this. It doesn't have any part where it's like this. In other words, why is it important for us in optimization? Because in convex function, we might have several minimizers. So in all of these points, here, 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 function is always minimum. However, in a strongly convex function, we only have one minimum. 1 point only is the minimum. I think, is it clear what I mean by strongly convex and convex function? Yes. Okay, please ask me if there is any ambiguity. What is Lipschitz smooth or Lipschitz continuous? You hear that a lot in the literature of optimization. It's nothing complicated. It says that absolute value of f of x minus f of y for any 2 points in the domain, x and y in the domain of function, f of x minus f of y, absolute value. It means that doesn't matter f of x minus f of y or f of y minus f of x, less than or equal to L. L is a parameter of Lipschitz. Okay, it's called Lipschitz constant times the second norm of x minus y. And when we say Lipschitz continuous or Lipschitz smooth, we can also call it L smooth. So 3 names for the same thing. And what does it mean? It means that geometrically, it means that the slope of function doesn't go high a lot. This is what it means actually. For example, here in this left figure, so x minus y, if it is a scalar input, so x minus y is this, right? This is a distance between x and y. This is the distance between f of x and f of y. Okay, assume this is the function. This is the line connecting this point to this point. So this is x f of x, this is y f of y. The line connecting these 2 points, and it's a slope. Its a slope is less than or equal to L. This function is L smooth, Lipschitz continuous with constant L. But this function, for example, it goes up suddenly and its slope becomes very high. Then you can see that its slope is not less than or equal to L. Or otherwise, L becomes very high. The upper bound on the slope is very high. Therefore, this is not a Lipschitz continuous or L smooth. Another example might be, not necessarily we don't need to have such cases. We can have like something like this. Okay, this function is the slope becomes close to infinite, close to a straight line. I mean close to this. So the slope is very high. It's not a Lipschitz continuous. When we say L smooth, it means that there is an upper bound, a limit on the slope of the function. So this, I want you to understand what L smooth Lipschitz continuous means. Okay, clear so far?
So it just means like it's one continuous line, like.
Yes, one continuous line, but there isn't a very huge slope too, right? If it's a very huge slope, it is still. So if it's not continuous like this, then it's not Lipschitz continuous at all. If it is like this, it's Lipschitz continuous, but with a huge L.
What about like a horizontal line? Would that be?
Horizontal line, you mean like this?
Yeah, yeah.
A function like this? It is a Lipschitz continuous. It is L smooth. The thing is that because the slope of here is 0, the thing is that why is it important in optimization, the L smoothness? Do you know why? Because it's very hard to optimize such cases. For example, what is the maximum of this function? That's why they usually make some assumption on L smoothness, and they use Lipschitz continuity in a lot of proofs for optimization. They usually assume that, and they use the parameter L in their proofs. Why? Because if it's not L smooth, it's too hard to optimize it. Do you get my point?
If it's not, it's hard to optimize it.
It's hard. Can you optimize this function? What is the maximum of this function?
Oh yeah. There's
Goes to
probably like
infinity.
two different things.
Yeah, what?
Yeah, like there's probably like two different maximum like there. So
Yeah, I'm saying that, for example, when it's horizontal, it's so easy to solve optimization for it. But when the slope goes very high, it becomes very hard to optimize it. That's why L smoothness is important in optimization.
Oh, okay.
Especially it's used a lot in the proofs. Get my okay?
Yeah, thanks.
Okay. Any other question? No.
Yeah, I had
Yes.
a question about the
Sure.
L smoothness. So you say it's a constant. So does that mean that for a given function, it'll be L smooth up to a certain L value?
Yeah, yes, a certain L value.
Okay.
No, we don't say up to, we say L smooth, for example, L smoothness with L equals something.
Okay.
Okay.
So
parameter.
how is that parameter determined when you're doing an optimization problem?
Yeah. First off, as I said, they usually consider it as a parameter and they use it in proofs. They usually don't determine its number. But I think there is a way I'm not aware of. I can look it up. But I know that there is a way. I heard it somewhere, but I didn't dig through that. But you'll see that, for example, in gradient descent, in several next sessions, when we introduce gradient descent, we'll say that the parameter L comes to the step size of the function. If you can calculate L exactly, then you can find the step function, step for the gradient descent. However, if you can't, you can approximate that. They usually approximate it. Its calculation, I think, is very hard. I think it requires some Hessian and these things. So it's very complicated. But I can look it up and we can discuss it next session. I haven't digged through that. Please, if you also find the answer, please let me know. Is that fine?
Yeah, makes sense.
Okay. But again, as I said, they usually use it as a parameter, not a number, a parameter in the proofs. Okay, preliminaries on optimization. So we talked about sets, we talked about functions, now we talk about optimization, minimum, maximum, and these things. A point X is in the domain is a local minimizer of function f if and only if. It means that it's two-sided. There is an epsilon, non-negative epsilon, that for every y in the domain, the L2 norm of y minus x is less than or equal to epsilon. If that's the case, what does it mean? It means that for the neighborhood of, this means that the neighborhood of the point x with radius epsilon, the neighborhood of point x, all of the points y which are neighbors of x, we have f of x less than or equal to f of y. It means that in a local neighborhood around x, the function value at x is always minimum, less than the function value at its neighborhood. This is local minimum, right? And so what if it is global minimizer? So that was local minimizer. If it is global minimizer, it means that for all of the points in the domain, f of x is less than or equal to f of y. So for all of them. An example is that this is local minimizer. For a neighborhood around it, see, this is minimum. All of the function values here are above this. This is also a local minimizer. This is not a local minimizer. This is a local maximum. So this is local maximizer. For a neighborhood around it, it's maximum. This is neither local minimizer nor local maximizer. This is a local maximizer because for its neighbors, its function value is greater than or equal to its values. Also, it's less than or equal to its values. So it's both local minimizer and local maximizer because it's equal to its values and it's in its neighborhood, right? But among, for example, these two local minimizers, this is also a global minimizer because in the whole domain, this is the minimum. So one of the local minimizers is absolutely a global minimizer, right? So a local minimizer is a special case of global minimizer. You can look at it in that way. And if we have a convex function, we'll talk about it. Okay, in convex function, any local minimizer is a global minimizer. We might have several local minimizers like this. When we have convex function, this is a local minimizer, this is a local minimizer, this is a local minimizer, all of these are local minimizers. But when we have a strongly convex function, we only have one local minimizer. And in convex function or strongly in convex function, all of the local minimizers are global minimizers. In other case, in convex function, we always either have this case or we have this case. If it's not convex, then for example, let me draw it in this way. Assume it's not convex. This is a local minimizer. This is a local minimizer. This is a global minimizer as well. But this local minimizer is not a global minimizer. But as this has happened because it's not a convex function. If it was a convex function, all of the local minimizers were the global minimizers. And why is it important? Because when we are optimizing a convex function, whatever local minimizer that we find, we know that it's this global solution. We don't need to search further because we know that at this if we find one of the local minimizers, that's it. We have found the minimum of the function, right? Okay, there is a proof for that, but I think because of the time limitation, I'm not going to that proof. You can see it in the tutorial as well, in our tutorial, as well as the next page that I have put in the annotated slides. But if we have time, I will come back to it and we'll go through it. Again, it's not in the exam for us to understand. It's just for us to understand why it's working. But let's skip the proof right now. You can read it, and if you have any question, please let me know. Another thing is that when the function, if it is convex and differentiable, it means that we can take derivative. The point x star is a minimizer if and only if this happens. It means that if a point in the convex function, if a point is a minimizer, its derivative, the derivative of function at that point is 0. Also, this is if and only if. It means that it's two-sided. It's if there is a point where the derivative of function at that point is 0, that point is also a minimizer. So both sides hold. So I think it's obvious why it's here. For example, this is a convex function. This is a minimizer, as you see. the derivative of this is 0. The slope of this is 0. Here, this is a minimizer. The slope of tangent of function at that point is 0. Here, this is another minimizer. The slope is 0. In other words, when we have a convex function, at the minimum, the slope of tangent to the function is 0. Right? And again, it has for side 1, it has a proof. If x is minimizer, then the derivative is 0. The proof, these are optional for you to understand. For another side 2, when the derivative is 0, then x is minimizer. Its proof is here. I think we don't have time for now to go through it. We might come back to it and we will discuss it. Okay. Some important points in optimization. One of them is a stationary point. One of them is extremum, which has maximum and minimum in it, and saddle points. Okay. So consider a function f in a general function, not necessarily convex. It might be convex, might not be convex. A point x star is a stationary if and only if its derivative is 0. So whenever at a point the derivative of function is 0, that point is a stationary point. And what is a saddle point? When we have a saddle point in a function, by passing through that saddle point, the sign of second derivative flips. What is the sign of second derivative? If the sign of second derivative is positive, the function is facing up. If the sign of second derivative is negative, the function is facing down. So this actually means that the facing of the function flips. For example, here, this point is a saddle point. Here, the function is looking down, facing down. Here, the function is facing up. At this point, the facing side of the function changes. This is a saddle point. In other words, in a saddle point, we have something like this. It might be you can also imagine it in multidimensional domain. If, for example, in 2D, it will be something like this. In this point, facing up and facing down. And what is minimizer or maximizer? If it locally or globally minimizes or maximizes a function. We already talked about that. Okay, and if it is minimizer or maximizer, we can call it extremum point. So extremum can be either minimizer or maximizer because it's at the extreme of the function. Okay, saddle point, the saddle point is not minimizer because the facing of the function changes. It's also not a maximizer. Although the gradient at the saddle point is 0. See, here the slope of the tangent to the function is 0, but it's not a minimizer or maximizer. Recall that I said this if and only if two-sided is for the convex function, right? But if it's not a convex function, it won't be if and only if. It will be only one-sided. So for example, here, it's not a convex function, but the derivative is 0. So we can, here also, these are derivative are 0. The slope of tangent is 0. So we can say in a general case, I think we have it here. In a general case, if x is a minimizer or maximizer, the derivative is 0. But if the other side is not necessarily true, if the derivative is 0, it's not necessarily a minimizer or maximizer. It might be saddle point. Okay, that's the case. It also has a proof based on the fundamental theorem of calculus. We will skip that proof for now. Any comments so far? No? Everything clear? Okay. Arguments of optimization. Do you remember? So for example, consider this example. I think it clarifies everything. The minimum of this function, can someone tell me what is the minimum of this function? Is
Like 2, 1.
no 2 or 1? Which one? So this is the input. Sorry, what?
2.
This is the minimum, exactly. So consider please note that this is the input of the function. This is the output of the function. When we say the minimum of the function, it means the value of minimum of the function, the minimum value of function, which is 2, right? What is the argument of the argument of the minimum of the function? Can someone answer?
It's 1.
Exactly, it's 1. In other words, the minimum of the function is 2, but the objective value, objective variable, the value of objective variable at the minimum is 1. All right? So now we draw it in this way. We write it in this way. So minimum of f of x, where the objective is x, but argmin f of x. When we put x here, it means that the objective variable, which we defined in last session, the variable of the function, is x. Okay. When we say min, it means the minimum value. When we say argmin, it's the argument of the minimum. We can have argmin or argmax, right? So again, I think this example shows what arg here means. Clear so far? Okay. So here also, before I show it to you, I have a question for you. So assume I have a function which I want to maximize, okay? But I only know an algorithm which can minimize. What are your solutions? Please let me know your thoughts. How can we use an algorithm which minimizes for solving a maximization problem? Is the question clear to you guys? Please
Can you repeat the
participate.
question, please?
So assume I have, I think it's better to write it down. Assume I have a black box and minimizer. Okay, when we give it the function f, it gives me minimum of f and argmin of f. Both of them. It gives both of them. Okay. Now I have a function g which I want to maximize. I think I need to reconnect. Just give me a sec. What happened? Sorry about it. Okay, can you see the screen right now?
Yeah.
Okay. I have a function g which I want to maximize. This function gives me minimum. I want to maximize the function g. How can I use this black box in order to maximize g? What are your thoughts?
By using negative value.
Okay, what do you mean, for example? Can you elaborate?
Suppose for x is equal to 5, it's give me a minimum value. So
Okay.
for x is equal to -5, it's give me a maximum value, corresponding maximum value.
Why do you say x equals -5? Why are you putting negative sign for x? This is my question. Your negative thought is correct, what you said about negative thing. But I think you used it in the wrong place. Why are you using it on the objective variable?
Could you use it on the function?
On the function, exactly. Exactly. So assume this black box gives me, so when I give it f, gives me this, right?
Yeah.
This is arg mean of f. This is mean of f. Now I want to maximize the function g, right?
Mhm.
I want to find it. If I give g to the minimizer, it gives me minus infinity because this goes to minus infinity. So it doesn't work. I want this. So I can flip g in a way that I multiply it by -1. Then if I give this minus g to this black box, it gives me the minimum here. And what will it be? It will be arg mean minus g. And do you agree that arg mean of minus g is equal to arg mean of g?
Yeah.
Exactly. What about mean of minus g? This is mean of minus g. How is it related to mean of g? Or to max of g? This was max of g. This is mean of minus g. Is that correct? Is
Yeah,
that
I think
correct?
so. Yeah, makes
So
sense.
what
Yeah,
is the
yeah, that's correct.
what is the relation of these two?
They both are opposite in sign.
Max of g is equals to min of minus g.
Exactly. Negative mean of minus g. These two, notice these two. These two are important. The same, you can say it for a black box of someone said their absolute is equal. Yes, their absolute is equal. But if the sign is important for us, then we need to take care of the sign. So we can have the same discussion for a black box, which is maximizer. It gives us max f, arg max of f. Then we want to minimize the function g. Again, minimum of g is equal to minus max of minus g. And arg max of minus g equals to arg min of
R max of
arg. Oh yeah.
R max of g.
Yeah, I think this should be max. Yes. Okay. This is one idea. There is another way to do it too. Can someone say that? There's another way to use this black box.
Can we do it in reverse?
What do you mean by reverse?
I'm not sure. I'm just guessing.
No. I think you have a good idea, but what do you mean by reverse?
Using reciprocal of the function.
Like if we are providing the function to the black box first. Instead, we can provide the variable to the black box, and we'll get the maximum of the function.
No, that's not the exact thing that's correct. But what you said stimulated someone else who said the correct answer.
Correct one. Okay.
Yeah. So someone else said, following you up, saying that let's give the reciprocal of the function. That's correct. Let's talk about that. So what do we mean? So again, this is a minimizer. We give it the function f. It gives us mean of f and arg mean of f, and we want to maximize g and arg max of g both. So what can we do? We can say So this is minimizer. This is the same black box. What we give 1 over G to that. It gives us some stuff. Now let's discuss what these are. For example, let me, oh yes. Assume, yes, I think it's a good idea to write it in this way. Give me a second. I'm designing an example. Okay. This is function G. Something like that, okay? 1 over x squared. And I want to find its maximize. Its maximum is what? Its maximum is infinity. Its argmax is 0, right? Now what is its reciprocal? 1 over G is x squared, right? If I feed this 1 over G to the black box, what does it give me? So its mean of 1 over G is 0. What is arg mean of 1 over G? No, arg mean is here, right? What x? It's 0
It's
again.
infinity.
No. What is the minimum of this function? It's 0, right?
0, yeah.
What is its argument? It's 0, 2. Okay, how do we relate these two to these? You tell me. Max of G, which is infinity, is
I
1
think
over, is that correct?
mean of G and argmin of G. Like mean of 1 by G
okay.
plus argmin of 1
Now-
by G.
Now let's talk about argmin and argmax. Did you understand what I meant by
Yeah,
min
yeah,
and
yeah.
max? Okay.
Yeah.
So now let's go to argmax. Argmax of G, what is it?
0. So that
No.
would be-
What is how is it related to argmin of 1 over G?
It's 1 upon argmin of 1 over G.
It's
No, it's directly
Yours-
related, I think.
I think it's exactly equal.
Directly related, yeah.
Why?
Because
Because wherever you're saying, someone was saying. Why? Someone also said something in the chat. Yes,
equal.
equal. Yeah. Why? Because wherever the 1 over G is minimized in the variable, I mean, in the variable,
Yeah.
the G is also maximized in the variable, I mean, objective variable. Okay, that's good. So now so 2 ways to convert minimization to maximization and vice versa. Okay, so I think I already explained these 2 ways. Okay, dimensionality of derivative. Consider a function. So what is derivative? Derivative of a function with respect to something else. So when you have a function with respect to a variable, before you read about this slide, listen to what I'm saying. This because I want to explain what derivative is. See, when you have a variable and you have a function, the derivative of that function with respect to that variable means that whenever you change that or tweak, you slightly change that variable, how much the function changes. Do you understand what it means? So how much effect the change of variable has on the function. Okay. Whenever I move that function a bit, how much effect it has on the function. This is the derivative of that function with respect to, or WRT with respect to that variable, right? So now assume the function is D2 dimensional and the variable is D1 dimensional. The derivative will be a matrix D1 by D2y, I tell you. I think by these examples, it will become clear. First, assume the variable is a scalar I think it needs to be variable. I will correct this. The variable is a scalar, and the okay, assume the variable is a scalar. F is also a scalar. What happens? It means that the function is a scalar output. The input is also a scalar. Whenever I change this input, it changes the output. Therefore, the derivative is a scalar too. The second example, I think, clarifies it better. Assume that now the x, the input, is a vector, and the function is a scalar. What would be the derivative? When we say the variable is a vector, it means that when you change every element of the vector x, it changes it has some impact on the function f. It changes the scalar f, right? So assume that x is a three-dimensional vector. I think with this note, it becomes clear to what I mean. Assume x is 1, 2, 3, and the function of x is a scalar. For example, x transpose x, right? It's a scalar. Now, whenever you change the first element, this epsilon might be positive or negative, and you don't change the other elements. This changes f. Now go to the second element, change it a bit, and don't change the other elements. This also changes f a bit. Do it for the third element. For every element, you change it. This changes f too. Is that correct? Now you tell me. So you have three options for changing x because it has three elements. And 3 times you changed f. Therefore, the derivative is a three-dimensional vector for each of these changes. This is for here, this is for here, and this part is for here. So when the output is now, the first example was when it is a scalar, and the output is also a scalar. Whenever you change this, for example, it changes f. Therefore, the derivative is one-dimensional. You have only one case where you can analyze, only a scalar. Let's go to the next page, another note. Assume x is three-dimensional, 2, 3, 4. F of x is also a vector. Assume, let me think. For example, this is x1. By x1, I mean the first element, x2, x3. Assume it is a vector where x1 plus x2, and this is tangent of x1 squared, x3 squared. So the function f is two-dimensional. The input is also three-dimensional. Clear? Now, so this is 2D. This is 3D. I want to see what is the derivative of f with respect to x. What's the dimensionality of the derivative? So the dimensionality of function is 2. The dimensionality of input is 3. Now let's see. First, I change the first element. It changes, let's call it f1, the second element of f2. It changes f1. It also changes f2. It might change. The change might be 0. For this case, the change is 0. But in general case, it might change, right? Also, now I go to the second element of x. I change it. I think if for you to understand what I mean, let's make it more. I want you to understand what I mean. Assume it has all of these cases. So this is F1, this is F2. Now, this changes F1, this also changes F2. Go to the third element. Changes F1, changes F2. How many cases could we analyze? So every element the change of every element of X will change or tweak every element of F. 1, 2, 3, 4, 5, 6. Six cases. In other words, 3 cases for input, change of input, 2 outputs we have, 6 cases. Therefore, the derivative will be 6-dimensional. This is what derivative means, that by changing the input, how much effect we have on the output, right? So, and we usually denote derivative with this, partial f of x with respect to x. This means that derivative of f with respect to x. This is 6-dimensional. Sorry. This is 6-dimensional, but there is a but here. We usually show it, we don't vectorize it. We usually show it by a matrix of 3 by 2. We can vectorize it and it becomes a 6-dimensional vector. But we usually have 3 rows and 2 columns. Why? The rows correspond to the number of elements of X, and the columns correspond to the number of elements of F. So far clear? Is it obvious? Any ambiguity?
It's clear.
Sorry, what did you say?
I said it's clear.
Okay, great. Thank you. So, in other words, the derivative of a scalar with respect to a scalar is a scalar. In this example now, the derivative of a scalar with respect to a vector is a vector. The derivative of a vector with respect to a vector is a matrix. Rows for the vector of input, columns for the vector of output. Now you tell me the derivative of, so here we had derivative of a scalar with respect to a vector. We might have a derivative of vector with respect to a scalar. When, for example, this is an example. We might have this example. X is a scalar, however, f of x is a vector. X and x2, right? This input is a scalar, output is a vector. So the derivative of this is a vector. Derivative of a vector with respect to a scalar is a vector. Derivative of a scalar with respect to a vector is also a vector. Derivative of a vector with respect to another vector is a matrix. Can someone tell me the derivative of a vector with respect to a matrix? What is it? So this is an example. If you understand this, you understand what derivative means. 2, 4, 5, 6, 7. This is a matrix. And assume this, but this is x1, 1. This is x2, 3, xij, I mean. So now assume the function is x1, 1 squared, and I don't know, summation of I1 to 2 x I3 squared, something like that. I want to say that this function is a vector. The input is a matrix. We can have different cases, right? So this is a 2 by 3 matrix. This is a 2-dimensional vector. What is the dimensionality of f of x with respect to x? Can someone say that? if you say this, so go with my example. What you tweak every element of this X and see the effect on every element of F, right? So what will be the derivative? How many cases will you have? Can you tell me how many cases? First, answer this question. How many cases will you have? This has 2 by 3, 6 values, right? 2 by 3. This has 2 values. How many cases do you have? Can someone say that?
12.
Exactly, 12. We have 12 cases. But we don't want to vectorize it. We don't want to represent it as a vector. We want to have it as a matrix format. So we know rows are for these, columns are for this, right? So the dimensionality of this will be what? Can someone tell me? This will be 2 by 3 by 2. 2 by 3 is for this, 2 rows and 3 columns of X, and this 2 is for this. Is that correct? So it will be a tensor. It will be a 3-dimensional matrix. It will be a cube, like a cube. Matrix is a 2-dimensional thing. It has rows and columns. And then you also have a height. Do you get my point? Is it clear now what I mean by the dimensionality of derivative?
Yes.
Yeah. Okay. These are what I explanations of what I said. Just the same thing. Now, this is derivative. We can take derivative of the derivative. So when we have derivative, it's called gradient. Usually, gradient is for when we have the input is multidimensional. When we say derivatives, usually it's like high school derivative. It means that the input is a scalar, output is a scalar. But derivatives is very general. But when we want to usually say that when the input is multidimensional, we call it gradient. So gradient is the same as derivative. You can look at it as derivative. And this is a derivative. And we denote it by either this or this, which is here is d-dimensional. Because output is a scalar, input is d-dimensional. Therefore, derivative is a d-dimensional vector. Gradient, right? If we take derivative of the derivative again, so we'll have a second derivative. When the input, we have second derivative, but when the input is a vector, usually we call it Hessian. It is a matrix. Why? Here, gradients was a vector because the input was a vector, output was a scalar. Input is a vector, but note that we are taking derivative of the derivative. This is a vector now. So the input is a vector. The input is a vector. The output is a scalar. Sorry, the output is a vector again. So the input is a vector in Hessian. The output is also a vector. Why? Because the output of the derivative was also a vector. Input of it is a vector. It's not a scalar anymore because input of it is a gradient. So input is a vector, output is a vector. Therefore, the derivative, the second derivative will be matrix with the same intuition that I explained in the previous slide. So we usually have a Hessian matrix. We usually have a gradient vector, and we usually have a Hessian matrix. And Hessian matrix is symmetric. Usually the conditions for making it symmetric holds in our cases. If the function is convex, Hessian matrix is positive semi-definite. It means that all of its eigenvalues are non-negative. If you don't know what eigenvalues are, don't worry about that. You can look at it offline and it won't be in the exam. Okay. Now, assume that the input is a vector, output is also a vector. So D one-dimensional input, D2-dimensional output, right? Then the derivative is usually called Jacobian. And this Jacobian, the derivative becomes a matrix now. So in the previous slide, gradient was a vector. Why? Because the input was a vector, output was a scalar. Therefore, the derivative is a vector, gradient. But now, when the input is a vector, output is a vector also, the derivative will be a matrix, a D1 by D2 dimensional matrix. Then we usually call it Jacobian matrix, which is a derivative again. Jacobian is another name for derivative, but when we have multiple dimensions. Okay, so far clear? There are some things I think I can leave these for interested readers. Let me exclude the slides. You don't need, these are optional. Don't need to read those. But if you want, we can discuss it later off class, because I think we won't have enough time to go through this. Just for your sake, if you want to learn about these are some equations where, for example, if we have this function, what is the derivative of this with respect to this matrix? These are some things that you can use for calculating derivative. I'll leave these to you as optional. This slide also, which is based on Kronecker product. You can look at these. Or ask me later if you want. We can have a session for discussing these. But these are I can leave them as out of a scope for interested readers. Okay. Chain rule. We have chain rule. So when we have a function, we can have a chain rule. If the function is you can write it as a function of function. For example, this function. Consider this function. F of x, the square root of x3 plus x squared minus x plus 10. You can write it as the square root of gx, where gx is this, right? So it's a function, a square root is a function of another function. Then when you can have this derivative of this function, you can have a chain rule. It becomes like a chain. You multiply several terms. In this way, now you have derivative of f with respect to g times derivative of g with respect to x. In order for you to understand it, although it's wrong mathematically to say that, but you can see that, oh, these two, you can cancel these out and say derivative of f with respect in the numerator, and you will have the derivative of x in the denominator. So to have this, to retrieve this, although it's mathematically wrong, but you can look at it as in this way. So in this way, derivative of f with respect to g, this is derivative of a second root. Its formula is this: 1/2 second root of input, and its input is g. Now multiply by the derivative of g with respect to x. Derivative of this with respect to x is this. Now you multiply these two terms, you replace x with what it is, and you will get this. So this is chain rule. Chain rule is also important in the derivatives. And vectorize, this means that when you have a matrix A by B, you can vectorize it to become a vector of AB dimensional vector. Example, 5, 6, 7, 8. You can vectorize it to become 5, 6, 7, 8. Right? Also, you can vectorize it inverse. So devectorize it to become again 5, 6, 7, 8. But when you devectorize it, you need to specify the dimension. So you retrieve the exact dimension that it had before, right? So also vectorization, you know what it is. Again, I exclude this for interested readers. You can read it and we can discuss it later. For just an example for calculating complicated functions we're using chain rules, and where you have the inputs are matrices. The inputs are not scalars. You can calculate that. So there are a few more things, but I think we are getting out of time. There are very few optimization problems, the forms. I think it will be less than 5 minutes to explain, and then we will go to linear programming in the next session. And I think yeah, I think we are going in with a good pace now. In linear programming, just before we end this session, linear programming is very simple. So let me show you, for example, this. Linear programming is a type of programming optimization where we can solve it using very simple ideas. It doesn't have a very hard mathematical way to understand it. So it's very visual, or you can imagine it. So it's very simple. So I'm saying that the next session, I think it will be an easy session, and you will have fun a lot about it, how to solve an actual optimization problem. So preliminaries are almost over now. In the next session, we'll go to linear programming, where, for example, we have such an example. Let me show you such an example. We have two variables to optimize it. We have some constraints, and visually, we can show the constraints. We can find the corners. We can solve it. And also, we will have some visual solutions. And then we will go and solve it using simplex method. And one of the methods that we use for solving the simplex method is a tableau method, which we work with tables. For example, like this. I'll show you some example. Like this. We'll draw some tables, and as you see, it's very simple and straightforward. It's like drawings, and we draw, and it has some procedure. We'll say, okay, first do this, then do this. It's just an algorithm, and it's very interesting. And an interesting thing is that in your assignment, you will also implement it in Python. It will be several lines of code. It's usually, I think, less than 10 lines of code. So it will be very simple, but you will code it, and you will see, oh, by your code, you could solve an optimization problem. And I think it will be exciting for you to have to code an algorithm in order to solve an optimization problem. And I think the algorithm, as you see, is very simple and straightforward. It has several steps. So this is our plan for the next session, linear programming. Okay, so any question? Can you guys let me know your feedback?
Yeah, no questions.
No,
No
looking forward to next class.
Okay,
It's good
great.
to me.
Yeah. Thank you, everyone. Whatever we said so far was required for you to understand the concepts of optimization. From the next session, we will see an actual algorithms for solving optimization problems for linear programming and integer programming. Afterwards, we go to the non-linear programming. Someone asked how we can find the last session video. I was absent. So you can find them in the course link. I put all of the links to the videos. We have both Zoom link, which I put, and it's kind of private. You can find its link in the course link. Also, I upload them in my YouTube channel. You can search my name in the YouTube. My YouTube channel comes. I think I can also, just give me a second, send you the link here. Yes, here, let me send it to everyone. So here I put also the videos of the sessions too, also in the Zoom. So you can see either in Zoom or YouTube. I will put the links in the course link, so you don't need to worry about it. Everything I will put on the course link. Also, we have a course homepage. Although all of the information, required information, is already on the course link, but you can also find the information on the course, not announcements, excluding the announcements in the homepage too, which is this. Send you. This is the course homepage, excluding the announcements. So the course link will be more complete. Okay, everyone. Any other question? Again, I emphasize that so far whatever we learned was for us to get into the algorithms. Someone says, does this course need any special requirement? I think knowing about a little bit about linear algebra and calculus is good. That's why sometimes I say, I hope you know what eigenvalue and these things, although I don't quiz you on these concepts, but it's good for you to know these linear algebra and calculus, simple calculus. But other things will explain why these algorithms work, so you don't need to worry about that much. Okay, and also your coding. It's good for you to know how to code in Python. You can practice in this course a little bit, so you can get your hands dirty on to know how you can actually implement some of the important algorithms, and it will be fun for you, I think. Any other thing that you need to ask? No?
Mhm.
Okay, great. We can, I think, conclude this session if you
Yeah.
agree. Yeah, and hope to see you next week, and we'll discuss the actual algorithms, start the actual algorithms. Okay, thank you very much. Thank you, everyone.
Thank you.
Thank you. Have a good time. Night. Thank you. Bye.
Thank you.
Thank you. Bye.